Welcome everyone to our first session. And our presenters today are Daniel Bristot and Gabriele Paoloni. Sorry, Gab, my apologies for mixing up your last name. They're going to be talking today about safety monitors inside the kernel. And with that, I'll turn it over to you guys.
Hey, so yeah, that's me. I'm Daniel, and this is the work that I've been doing with Gabriele. Each one working on its own straight. And here is the result, which is running safety monitors inside the kernel and the safety analysis required for it to be part of the safety critical systems. So I will start with an introduction of some research, and then we will go to the, let's say, to the making the runtime verification things practical first. So introducing runtime verification is a lightweight yet rigorous formal method that presents a practical approach for more complex systems. Because instead of relying on creating a complete model of the system, we work by analyzing the system as it runs by observing the trace of it and comparing the trace against a formal specification of the desired or undesired behavior. So the main advantage of RV is that we can observe the actual runtime behavior of the systems without the pitfalls of having to develop models of the system itself. Given an efficient monitoring method, it's possible to execute this runtime verification online as the system runs, and actually also synchronous to the system in such a way that if some unexpected behavior happens, the monitor can react promptly and going, for example, to a fail-safe mode without delays. So understand a little bit the components here. So in one side, we have a Linux, and we observe Linux as a trace of the system. And the other side, we have the formal realm, where we have a formal specification of the desired behavior, right? And the REV connects these two things by using system instrumentation from tracing and trying to run this formal specification as the system runs, right? The monitor, which performs this comparison, it might just run the specification and say, okay, things are running fine, or react to an unexpected behavior on multiple ways, like creating a warning and telling us to fix our model if our model is not correct, or giving a successfully stressed model. We can use it on a safe critical system, putting the system, for example, into a fail-safe mode. There are multiple ways to do runtime verification. There are multiple formalism, but in this case, we are talking about one formalism, which is automata. It's a well-defined formalism. Let's say probably is the most well-defined one, and it has its formal specification, right? We can do operations, we can automatically check it, but for really humans, it has a good property, which is having a graphical representation that we can clearly see the model and try to understand it, for example, as well as using automatic methods to verify if the model is correct. Talking about a proof of concept of these ideas and the research that involved, we, during the last years, have been doing research on how to use automata to model complex behaviors of the system. And I successfully create a model, for example, for the pre-NTRT synchronization, which is a huge model, right? It has more than 90,000 states and more than 21,000 transitions. And it was possible to do with automata by building the complex system from small specifications, right? From pieces, from 2 or 3 states. In the worst case, there is one of 10 states, but just one among them. And there is a publication here if you want to find more about it. Also, So modeling is one part. The other part is trying to verify if the model and the kernel are matching one with the other. And there's also research where I developed a way to translate a formal specification into code that I can compile into the kernel and then run the model inside the kernel as the kernel runs, right, synchronously. And there's also a research published about it. You can find more information there. One good thing about the approach presented in this paper is that it showed that if I just run the, the automata inside the kernel, like this SWA, which is one model, by running the automata inside the kernel, yes, the system runs slower than the system not monitoring it, right? But it runs still faster than just by tracing the system. So in this case here, I went to the ftrace directory and say, I want to trace these events. So this is the result of the just tracing it. And this is the result of actually running the automata inside the kernel. And the reason is that running an automata inside the kernel is faster than getting the data and saving it to the trace buffer. And that's one good thing, because even though we can see that there is a performance degradation, it's normal when you add more code. It's still faster than doing trace, which is something that we have even in production systems, right? We can enable tracing on production systems, so we are causing less damage than just tracing. Yeah, that was more a research part, right? The basis of what I'm working now, trying to add it to the kernel as a kernel feature, right, or as a subsystem. And now we are talking about not exactly a research, but the development of this research as a kernel feature. So recalling that diagram that I showed, that you have a formal realm in one side and the Linux realm in one side. Now I'm giving names for these blocks here. So the RV subsystem is an interface and a set of tools that make runtime verification accessible for developers and for users, right? An RV monitor is composed of a model or specification, right? And the instrumentation. The model is the formal specification of the desired or undesired behavior, and the instrumentation is the part that connects the monitor to the tracing part of Linux, right? And then the monitor connects the two things. And the reactor, it is an action that's called on when something wrong happens, when some unexpected event happens. And the monitor can cause a reaction. In the, I will show a video where I show actually using the interface, but in the interface I will show there is the reactor, is the action that I will take, and the monitor is this all together, right? The instrumentation and the model running together to monitor the system. And each monitor can have one reaction set. It can say, I want to run the monitor, but I do not want to react, or I want to run the monitor and have this specific reaction when something bad happens. But this thing will get more get easier when I show the demo. Full screen isn't available. Wait. Why is it running the full screen? Is there any Zoom expert that can show me how to run? Oh, here we go. So here is a video where I show me running the RV interface. So I will join to the tracing subsystem, and then I have the RV directory there. And here I have some files and directories. This interface, whoever have already experienced the tracing interface of Linux kernel, it resembles the tracing interface on purpose, and I'm placing it as part of the tracing subsystem. So here I'm listing the available monitors in the system, And here I'm listing the available reactors in the system. Here I'm saying that there is no enabled monitors. And I'm showing that the system can be monitoring, can monitor things, and the system can react. These are on-off switches, like tracing on in the kernel. So I'm saying here that I want to enable the WIP monitor. You see, now there is one monitor enabled. I can disable the WIP monitor, and then I see there is no monitor enabled anymore. I can join on the monitor folders, and I will see one folder for each monitor. And here's the safe watchdog. There's a description, and Gabriele will talk more about safe watchdog later. It's not enabled, and the no operation reactor is selected. So I'm saying here, okay, I want to react doing a print K when I run this monitor. You see, now it's print K selected. And I can enable the monitor. It's enabled. And then I can go back to the tracing directory of the system and see the events that are available, right? In the tracer subsystem, I'm not even on the RV subsystem anymore, but I can see that I have trace points for each of these monitors, right? So I'm saying here, I would like to see all the events generated by the monitor. And my system is not showing anything yet because the monitor is enabled, but I'm not exercising the watchdog subsystem, right? The monitor enabled was the safe watchdog that we'll talk later. Here I will dispatch a tool that will use the watchdog. It opened the watchdog, closed, and you see, here's the RV monitor. Oops. And here's the RV monitor. The RV monitor generating the events that it followed, right? It was an initial state, there was an open request, and the model went to open, and so on. But we will talk more about it later. So that was the part where I was using the subsystem. But let's say I am a developer and I would like to develop my own monitor for my own use case, right? How can we make this easier? So the RV interface also adds a way for one to translate an automata from the .vis format, it's an open format, into a kernel monitor. And there is one utility that I'm added on the patchset, right? Hopefully one day in the kernel. And this utility, it creates a skeleton of an RV monitor module. There is also a set of C macros that resembles the trace point constructions on purpose that generates the monitor code based on some informations I give about this monitor. And the only thing left for the developer to do, given a automata monitor, is to do the instrumentation part, which is saying, I would like to connect this kernel event to this automata event. But there is also a demo video here. So here's one example of an automata, right? This is the automata. And I'm saying, oh, here's the dot file, right? Saying this is the automata I would like to transform. Here's the tool and some options that it has. I can say the type of the monitor, like if it's a global monitor, one monitor for the entire system, or if it's a per CPU monitor. In this case, it's a global monitor. We have one watchdog for the system. This is the name of the monitor that I would like to have, and that's the model. Bang, it created the files. And say that it gives instructions for how to proceed, right? So Here I'm showing some files. This is the automata transformed into C code. This is the definition of the trace points where I can observe this monitor running. And here is the monitor itself. This declaration here, right? This is the macro that will expand the code and define the entire monitor, the entire structure of the automata monitor in the kernel. And it uses macros to do automatic code generation in such a way to reduce, in one hand, reduce the amount of code for each monitor, but also to reduce the problems of the development, right? Because if I had to develop by hand each monitor each time, I might as well have different implementations of monitors by adding bugs myself. Here I'm using this macro to consolidate all the code into a single implementation. It's also, I'm not using functions, I'm using macros because I want to make all the modules completely independent from one from the other. So the functions that will define the model here, it will be exclusive for this file. So here I'm including the trace points. And this is the instrumentation part where I say, okay, these are the handlers of the kernel events. Please connect them to the automata events. And here is the part that you see there are a lot of nodes saying, okay, do this thing here, do that thing there. And that's it. The complexity is all hidden by the macros and by .2k. Sweet, Daniel from the past. And yeah, and then here I pass the work to the other part of the equation. Gabriel?
Okay, so thank you, Daniel. So after you saw the overview of about what is a runtime verification monitor, how it is designed, and how it is used in practice, let's see how this guy can be used or useful when it comes to a functional safety claim, right? So the key question here is, how do we envision the runtime verification monitor as a possible safety mechanism? Okay, so next slide. Okay, so let's give it a bit of a context here. Okay, so during our investigation in the architecture working group, we examined the telltale use case that is where we have a safety application that is working periodically, okay, to meet a certain FDTI constraint. So it means that there is at every period there is a maximum time to completion, okay? And in practice, the way we monitor the safety application to complete on time, it is through a watchdog mechanism at every period. Okay, so if the application is late in petting an external program, the watchdog, then the watchdog itself will trigger, and therefore it will drive the system into safe states. Okay, so given this context, you can understand that it is critical to have the watchdog to be programmed with the correct timeout and to be working continuously according to the timeout that has been set. Okay, so next slide. Okay, therefore, from a system level point of view, there are some high level safety requirements. Okay, and these safety requirements are the following. Okay, so the watchdog FDTI timeout shall be programmed before the safety operation, and the watchdog shall be started before the safety operation according to that timeout. The watchdog shall not be stopped during safety operation. And also the watchdog timeout shall never be changed during safety operation, okay? And with respect to these requirements, our goals are to qualify the VFS and watchdog subsystems according to the above requirements, and also to enforce freedom from interference between the qualified subsystems and the rest of the kernel. So these are two key goals that we would like to achieve, right? So next slide. Okay, good. So if you remember what Daniel said previously, what is a runtime verification monitor? So a runtime verification monitor is a subsystem, is an element that is running in kernel mode, okay? And that is monitoring a predefined subsystem to behave according to the architectural model that has been formally specified, okay? So basically there is, a sequence, a state diagram, okay? And if the monitored subsystem behaves according to that machine state diagram, then the monitor will be happy. Otherwise, an exception will be triggered. What does it mean? In practice, it means that we are, from a functional safety point of view, we are realizing an ASIL decomposition effectively within the kernel itself. Okay, so and more specifically, the flow that we are, that we follow when it comes to the watchdog monitor is the one that is depicted in this slide. Okay, so the first thing is that the safety requirements are allocated to the monitored subsystems. Then we have decomposed safety requirements derived for the runtime verification monitor that are based on the top-level safety requirements. We have a safety analysis that is conducted over the possible failure modes of the monitor subsystem. This is to confirm the decomposed requirement allocated to the RV monitor. Okay. Then we have, the RV monitor that is designed using the formal architectural model in an automata format, as Daniel mentioned previously. Okay. We have an FFI analysis between the RV monitor and the rest of the kernel. Okay, and this could eventually derive additional requirements for the design of the RV monitor. Okay, and finally, once we know that we met the two safety analysis goals, then we have the final design for the RV monitor. This is automatically compiled, as Daniel showed in the previous slide, and it is automatically compiled in a full independent implementation, okay, compared to the monitored subsystem. And this is very important, because in order to meet the ASIL decomposition requirements, we need to have a full independent implementation. Okay. So next slide. Okay, so let's have a closer look at the first requirement decomposition. Okay, on the left, I'm listing down again, the top-level safety requirements that are allocated before decomposition. Okay, so the FDTI, the watchdog FDTI timeout shall be programmed before the safety operation. The watchdog shall be started before the safety operation. The watchdog shall not be stopped during safety operation, and the watchdog timeout shall never be changed during safety operation. Accordingly, we have decomposed safety requirements for the monitor, for the watchdog monitor, so the watchdog monitor shall detect if the FDTI timeout is not set before safety operation. The watchdog monitor shall detect if the watchdog is not started before safety operation, or if it is started before setting the FDTI timeout, the Watchdog Monitor shall detect during safety operation any event that will stop the watchdog. And finally, the Watchdog Monitor shall detect during safety operation any event that will change the watchdog timeout. Okay, so in principle, these are, this is a pretty simple decomposition, right? There is nothing special here. So we can go, to the next slide. Not coming up. The next slide. Okay.
There's a delay because I'm placing them and it's taking a while for it to reply.
Okay, good. So this is okay. So this is basically the the design of the Watchdog Monitor architecture following the allocated decomposed requirements. Okay, so you can see. So the first thing here is to mention is that you can see there is a red line in the middle of the diagram. Okay, so this red line is dividing the possible state machines into two state machines effectively. Okay, there is one on the left and one on the right. Okay, the reason for this is that in the Watchdog subsystem there is a parameter that is called no way out. If this parameter is set, okay, the watchdog is not allowed to be stopped once it is started. Okay, and accordingly, there are two states machine that are possible. Okay, so this is the reason for for this high level split. Okay, another thing to notice here is an event that is called other threads. Okay, so these other threads events identify the possibility of a thread different from the safety application to manipulate the watchdog. And the monitor allows this to happen only in certain states, okay? So, for example, when we are in the safe state, this is not allowed, okay? So if another thread manipulates the watchdog, bang, we have an exception, okay? So this is a violation of our safety requirement, okay? Then we have, we have the init state, okay? So this is the initial watchdog state following watchdog init. We have open state, the watchdog state following watchdog open. We have the started state, that is when the watchdog has started according to the default timeout. Okay, that is, and it is a timeout that is different from the safe timeout, from the FDTI timeout. Okay, then we have the set state. Okay, when we have set the correct FDTI timeout. After the set state, we have the safe state. Okay, when the watchdog is finally running according to the newly set safe timeout, and at this stage, the safe application is good to start, the safe operation, because we know that at this stage, the safety application is being monitored, okay? And then we have, finally, we have the close the running. So this is basically when the watchdog is released when it is still running. And then we have the stopped state, that is, when the watchdog is stopped, that following a call to watchdog stop, okay? And this state is not reachable when no way out is set, because by definition, no way out enforce the watchdog to be not stoppable, effectively, okay? Okay, good. So I think that, this is a bit, some time is needed, to digest this diagram. So maybe, we can talk about this, more offline eventually on the mailing list, whatever. Okay, so but maybe let's go to the next slide so that I can present in principle the effectiveness of this monitor doing a high-level safety analysis. Okay, so please, next. Okay. Okay, good. So let's have a look at some of the failure modes. Okay, so here, so the failure mode is that a safety application invokes the syscall to set the timeout, but for some reason, this event never reaches the Watchdog subsystem. Okay, so effectively, the Watchdog FDTI timeout should be programmed before the safety operation, and the safety app could. The hazard is that the safety app could start the safety operation with a Watchdog timeout not set, so effectively being unmonitored. Okay, and the detection mechanism here is that the Watchdog Runtime Verification Monitor, can be the safe state, can be retrieved at any time from the safety app through the traceFS. Therefore, following the ioctl invocation of the safety app, so following the ioctl invocation, the safety app can verify the monitor to be in the correct state. Okay, and this is a mechanism to guarantee that this failure mode is detected. Okay. So next one. Oh, what a delay. We need a watch to consume.
10 seconds passed already from the time you press
okay.
next.
Yeah. So this is not safe. Anyway, so this is the second failure mode. Okay. So let's assume that for any reason, for any reason, the Watchdog subsystem does not follow the correct sequence of events from init to save. Okay, so if you remember, if you look at the diagram, there is a sequence of events before we end up in the safe state and we can start the safe operation. Okay, so what if there is a spurious event like a ping, for example, here that is happening from the started state. Okay, in this regard, so the requirements that are violated are that the Watchdog FDTI timeout shall be programmed before the safety operation, and the Watchdog shall be started before the safety operation. These are the two requirements that are violated. The hazard is that the Watchdog could start misbehaving. Okay, who knows? And the detection is that the Watchdog Runtime Verification Monitor will detect any such event. Okay, if this happens, an exception will be raised, and the system will end up in safe state before safety operation. Okay, so we'll be safe with a disappointed driver probably, but safe. Okay, so next slide. Okay, another failure mode, something that we already mentioned. So let's say that a thread different from the safety application starts to manipulate the Watchdog. Okay, and the requirements that is violated is that the Watchdog shall not be stopped during safety operation, and the Watchdog timeout shall never be changed during safety operation. Okay. The hazard is that the Watchdog could be disabled. The timeout value could be changed, right? So this would lead to the deactivation of the safety mechanism. Okay. How do we detect that? So you can see in the green circles on the left that the monitors only allow different threads compared to the safety application to manipulate the Watchdog. So this is allowed only in specific states. Okay, so that is when the Watchdog is closed or in the init states. In any other states, another thread manipulating the Watchdog would result in an exception, and again we would have the safe state being driven. Okay, so the car will pull over probably. Okay, whatever. Okay, so next slide. And now this is an interesting failure mode. So let's say that we have a QM kernel code, okay, that for any reason is overwriting the watchdog timeout, right? So this is a typical, spatial corruption, okay, that could happen in the kernel address space, okay? And what is the requirement violated? The watchdog shall not be stopped during safety operation. The watchdog timeout shall never be changed during safety operation, okay? The hazard is that, the watchdog could be disabled. The timeout value could be changed, okay? So leading to the activation of the watchdog safety mechanism. The detection is that, as you can see in the code, the watchdog monitor can be configured to retrieve at each ping the physical time left from the hardware watchdog underneath. So if the time left is bigger than the safety timeout, an exception is triggered. Okay, so this means that every time the safety application pet the watchdog, we can verify, the time left to be less or equal. Okay, and we know that we are being monitored in that safety cycle. Okay. Next. And now, so this is something that we are still working on. So effectively, we presented high-level safety analysis that basically confirm the effectiveness of the watchdog the effectiveness of the watchdog monitor as a monitor, of the watchdog subsystem failure mode. Okay, so now the question is, we also know that the monitor itself runs in the kernel address space. So how do we protect the monitor from the kernel itself, right? So this is, the problem. Okay, and next slide. And there are some ideas here. Okay, so one option could be that the runtime verification monitor states could be stored in a read-only memory area. Okay, so that if the kernel overwrites the memory, the SMMU would raise an exception. Okay, or another option would be that to store the runtime verification monitor states using end-to-end protection. So, and the idea is that at every pet, the runtime verification monitor can verify the current state to have not been corrupted by, verifying the associated CRC, and also when the safety app interrogate the monitor, to verify the states, can also, do a CRC check. So this is quite an effective measure, against the spatial interference on the RVM data. Okay, so right now, if you look at the current RFC that Daniel submitted, we don't have this protection in place yet. But
yeah, we have the first. The states are stored on a read on the memory, but we don't have yet the second.
Yeah. Oh, sorry. Sorry. My fault. So we have the first. Okay, great. So next.
Yeah. So just showing a demo of how we envision like an application enabling the safety monitor and comparing the execution of the safety monitor and closing the loop, right? So we expected to see the system being used like with an user space application that controls the watchdog via the watchdog interface, right? The application enables watchdog and periodically pings the watchdog upon the correct completion of safety-related processing. And this safety app, which is a skeleton tool, let's say, that can be used for other applications, it uses the RV monitor, right? It does the watchdog configuration, but it also uses the RV monitor, the safe watchdog, the monitor that Gabriele explained, to see if the monitor is running itself, to cross-check one thing from the other. So it sets up the RV monitor and gets feedback from the RV monitor. So then here is the one example. How do we see this in practice? This is also part of the RFC. So here I have my system, and I have this saved, this demo application, the saved app, and I say I can set up the Watchdog, I can set the timeout, set if I want to, which kind of monitor I want. And here I'm using a reduced version of the model that always enforces the usage of no way out. So safety app, as we see, it's running, and then I simulate a crash of the application. Then we'll see the Watchdog reacting, right? This is what the Watchdog detecting, like the system failure, and the Watchdog detected a failure. Now we'll see the other way around, when the people using when the application using the Watchdog misuse it. So now let's use the no way out monitor, which is this automata here is just part of that automata that Gabriele showed, which enforces, like, it always needs to start setting the way out before, for example, opening the Watchdog. So I would special save the app, and I will set that monitor I showed, and I will set the timeout, but I will not set the no way out before starting opening the Watchdog. So here, bang. The RV monitor catched a problem, which is the safe Watchdog monitor, safe Watchdog no way out, does not allow the event open in the initial state. That's a side effect of not using the no way out feature. In the initial state, I always need to set no way out before. There's more to come on this video is the stats on the RFC v3, and there is more to come. So we are in the RFC v2, the submission of the patch. There's a good consensus around the patch so far, right? We never know. And it includes the interface, the monitoring director's base, the monitor synthesis, and the saved app. And we are working on a v3 right now. And that's it.
Thanks. We've had a lot of good questions coming in on the chat. Are you guys able to see it and maybe start to respond to some of them?
Yes. So we have, so the first question is, how is it ensured the RV automata inside the kernel does not interfere intended behavior of the kernel timings of system? Okay. The second, okay, the first question is, so in I think so Daniel already presented, so I will give you first a qualitative answer and then also an answer from a safety perspective. Okay, I think that Daniel already showed that the performance impact of having the runtime verification monitor enabled is very, very low. Okay. So, and this is like the common sense answer. So we know that by measurements that the impact is very low. From a safety point of view, we have presented a use case that guarantee the timing requirements of the safety application through an external watchdog. Okay, so then what happens? Okay, so the monitor is monitoring first the subsystem of the watchdog to move successfully to the safe state. The safe state is when the watchdog is running according to the configured timeout. At this stage, we know that we have an external hardware monitoring the on-time completion. So at this stage, we don't care, if the runtime verification monitor timing impact, is bad for the safety application, because we know that we have an external safety measure. Before we reach the safe state, we don't care, because what happens in practice, by definition, we cannot start the safe operation if we have not reached the safe state. And what we did show in the safety analysis in the first failure mode, that the safety application, after setting the safe timeout, can retrieve the status from the runtime verification monitor to make sure that this safe timeout has been programmed and that the watchdog is also running. Okay, so we have a system level measure, to check, the external hardware mechanism, the watchdog, to be properly configured before starting safe operation. The runtime verification monitor is the guarantor of that, of that external hardware to be properly configured. So this is the answer to the first question.
Just on top of that, to run the automata, I just run an O of 1 operation. In this O of 1 operation is read a variable and write a variable. We can't get better than that. But yeah, that's it.
Yeah.
And also, it only adds overhead to the things that we are monitoring, right? In this case, we're just monitoring the watchdog. So we are only causing impact in the application running the watchdog, not in the overall system. So it's as good as it can get. Yeah.
Okay, then there is, second question is, in some cases, there may be a lot of events in the system. Is there a inbuilt mechanism which can indicate overflow of events? I don't understand that. Why would
we don't have this problem, because we are not doing in the runtime verification, we have online synchronous and online asynchronous. In online asynchronous, you write the trace to the trace buffer and you collect it. Then you can have this problem of buffer of events. But in this case, we're not using a buffer. When the system runs, it stops the execution and it runs the automata. So I don't have a buffer to overflow. It's synchronous to the system execution.
Yeah.
But Daniel, then isn't it you are kind of preempting the normal functioning of system and doing a verification?
Yeah. Okay. To the I'm cross-checking, right? I'm writing it to the buffer. Yes, there is this another part. Let's think on it. Yeah, that's a good example. So on the safety application, we are using the buffer. You're correct. In the safety application that I showed there, I write it to the buffer and then I read it in user space, right? One thing is that the level of events that we are using there is really small. We will hardly fulfill the buffer. But if we fulfill the buffer, we can capture this, one, by seeing from the user space that there is something that was not expected in the kernel. And two, when we add the CRC, that the thing that Gabriel mentioned, we will add a counter, because we need a counter for CRC. So we will be able to see that there is one event that we missed, and we could detect this problem with the buffer. That's a good question.
Okay, and then there is the third question is just for you, Daniel. What is the source for drawings of automata?
Drawing automata?
Yeah.
There are many tools where you can use to draw automata. I personally use one that is
Daniel, can you take a pause? Let me give more context of this question. So you are verifying certain things, right? Against what? Is that the code, or you have some prescribed design against that we are going to do the verification? So especially why I ask, because most of the time, right, Linux is kind of a source code that is existing, right? So if we are doing a verification against the code, right, I don't think that meets the intent of safety.
No, what happens is that there is a tool that is used to draw the automata diagram, okay? So that diagram is your source. Basically, you use a formal method, a formal architectural method to impose a behavior on a monitored subsystem, okay? That diagram is then automatically compiled into runtime code that is completely separate from the subsystem that you are monitoring.
Yeah.
I think you are going towards the syntax and semantics of drawing automata. I'm asking one step backward, right? What you have taken as input, right, to come up with the automata? Is that there are set of requirement or something of that sort, or it's the source code that you have already there?
You mean from where did we took the rules that we designed in the monitor? The
No,
specification,
the automata, that's the input for your verification, right? So you draw certain, right, call sequences, correct? And that's automata. And then this automata is translated into a RV. And against that, you do a verification. So my question is that, is the generation of the automata, is that driven from the source code or is driven by set requirement?
It's driven by the developer. That Watchdog monitor, it was designed by me and by Gabriele. It is manually designed.
Yeah. It's a new design, basically.
There's one paper that I mentioned here. This paper, it explains how you design and synchronize small automatons to create big ones. And it shows how we can scale all that. But so far we're doing now manual because we need to understand what we're doing. Maybe in the future there will be automatic code, automatic model generation. And I know papers for people in Oxford doing that, but still earlier. And we still don't need it, but there are people researching it for the future already.
Just to be clear, I think what you're saying is that the model's intended to represent your requirements for the system. So you're using it to verify them, so that you obviously need a set of requirements as an input to that model. Where do those requirements come from?
Yeah, these are the requirements that you also present in this presentation, right? They decompose the requirements.
So you need a set of safety requirements for your subsystem that you then represent in the model, and you compile the model to
Yes.
create the monitor. Yeah.
Yes, exactly.
Perfect. Yes, perfect. That's it.
Yes. Okay, so there is the question from Elana. I think we already answered that. So she said, do you have any data on runtime performance impact?
There is this paper where I explain that. It explains the algorithm for verification and some examples of performance measurement.
Okay. So then there is another question from Sanjay. Can you please re-emphasize the independence argument as stated in slides? I think, yeah, we already described that, right? So we are completely independent because we start from a newly developed architectural model, and the model is automatically compiled into the kernel itself. So, and therefore is a completely independent implementation allocated, you know, with separate requirements. So then another question from Paul: can you show some examples of runtime verification instrumentation and explain how the global macro implements safe access to the monitor within the kernel. Yes.
That's the part that Gabriele and I were explaining, that we need to put a CRC in the variable and to check that still needs to be developed. It should not be a problem.
Yeah.
But yes, now it's just a read and write to a variable. There is no protection, and that's the thing that we mentioned, that we need to add this thing.
So you effectively, you have a global variable that provides the linkage to the monitor. Wherever you are in the kernel, you can have access to that monitor. And because you're executing synchronously, you don't have to worry about it. But okay, are there not threads of operation within the kernel that might mean that you actually need some protection there? Is there any state within the monitor that you're storing? So if you have kernels on kernel operations on different CPU cores, you could have kind of some potential conflicts there.
Correct. We now have a global variable. It can be accessed by any thread, any interrupt, anything running inside the kernel. Yes, but that's the is to do here.
Yeah, but the thing is that when it comes to data corruption, the end-to-end will make it, right? So basically, we'll be able to detect that. And when it comes to so if the question is that, so how do you protect the monitor from time interference or something like that? So effectively, so we could rely on the external watchdog, because once you know that the watchdog is programmed correctly, you know that you are being monitored, right? So if everything halts, the safe operation, so you're fine. Or you could have different RVM to monitor the interrupt latency, but that's a different story. So this is not covered here.
Yeah, I think I can see how this would work for the watchdog use case, assuming that you've just got a single application and you're kind of not worrying about different threads of operation. I guess what I'm wondering is, as a general model for implementing this kind of thing in the kernel, I wonder if it's kind of scales to kind of more complex use cases, or whether it's limited to this kind of use case where you already have a kind of a safe state transition that's being provided for you by the external watchdog. So you've got that kind of fallback. Have you kind of given a thought to what are the limits of this approach to the kind of subsystem it could monitor?
I think, well, I mean, we are thinking about that. I think there is some room to possibly scale to. So in my view, the limit is that, yeah. So Daniel.
I mean, there is multiple dimensions when you mention scaling, right? If you want to protect the access against concurrent access running the same model, yes, we can add the synchronization. If we want to scale a number of states, the transition will still be of one, and there is an example of a big model. There are multiple dimensions where we can scale. So which dimension are we discussing?
That's it. I was aware that there were all these different dimensions. So I just wondered which dimensions you'd given some thought to. But thank you. I think you've answered my question.
So if you think, just trying to exercise some dimensions, right? How complex is the model that we can verify? Because the operation is O of 1, we only increase, it's independent of the number of events and states that we have inside the monitor. So we can monitor really big automatas. And there is one paper that I show a really huge automata. Because we resolve these problems during modeling phase. It's this paper here. This paper shows a very huge automata. Another problem is that, for example, let's say I can scale on the type of monitor. For example, I support now global monitor, per CPU monitor, and per task monitor. So if I have a per task monitor and only that task access the monitor, I don't need synchronization because it's the task itself, right? If it's a per CPU monitor like this one, the per CPU, the thread synchronization, I don't need synchronization. If I have a global monitor with multiple threads that might access that monitor, right? I might develop a type of monitor, a specific type of monitor of the type, for example, global synchronized, and I can protect it with a spin lock, for example. And as we add more synchronization, we might have more impact on performance, if that's correct. But each monitor is independent, so not because I have one monitor that I need synchronization, that will impact in the other. So far, all the monitors that we have doesn't need synchronization, so we are still on the good place. But well, we might need synchronization in the future, and then we need to see how to address those problems. So far, we don't see the need. Just a last comment is that generally the thing that you would be monitor, if there is a chance of concurrence, there's generally already a protection around that piece of code. For example, if I want to monitor the inner part of a real-time mutex, the inner part of real-time mutex are already synchronized with a spin lock. So generally, many times we'll be able even to reuse the synchronization already in place. But yes, we might need to have a monitor with protections, and we can do that.
Okay. So we are out of time, but there are other questions. So now I don't want. I mean, I don't know if if we want to answer these questions, taking a bit of a time from the break, or.
I suggest keep it going when just, like I say, it's just overlapping with the break. The other thing is we could potentially reconvene in the break room because people can click on the break link and move into that room if you want. But you can, everyone's here, so you may as well just keep going.
Okay.
As long as people are.
I can go for more 10 minutes because I need to go to another meeting in 2 minutes.
Oh, in 2 minutes. Okay. So maybe just one more question. So from Lucas Lansky, how is it ensured that the Watchdog Monitor itself actually executes? Isn't it also being scheduled by the only QM Linux scheduler?
It runs synchronously with the application. It's not a thread running. It's not a hierarchy. It's like this. The safety application is calling the code of the Watchdog. Then it hits the open operation. This open operation there is a trace point that was the patchset added. This trace point will be executed, and then the thread is still in the context of the safety application. This trace point will be executed, run the automata, and then continue in the execution. So there's no scheduling involved. It's in the context of thread running the code.
Yeah, exactly. So the next question from Igor Stop, what is the model of interference that can be detected by the automata model? So I would say that mainly spatial and communication interference. Basically, anyway, it would be any interference that would lead the monitored code to behave not according to the formal model enforced by the monitor itself. Okay, so I would say mainly communication and spatial interference, whereas for time interference we need to rely on a different monitor that can be the external watchdog or possibly another runtime verification monitor, but
with the timer.
Yes, strictly focused on the latency monitoring.
Yes, I'm working on verification methods with time. But we need to walk before I can run. So far we still don't need it, but we are working on research on that part.
What I had in mind though was if there is a special interference which alters a value in a way which is still compatible with the possible range of values, would that be detected? Does it depend on how I implement the model?
You can, let me see if I understand. You can, the type of event can be anything you interpret it. It's a very abstract. You can say finish before the deadline and finish after the deadline. So you can have
what I had in mind is, let's say that I have a stored value in a device driver which is 5, and
Okay.
all the acceptable values go from 0 to 10. There's some interference, the value from 5 becomes 7.
And who is
So it
causing
has
this
changed,
interference?
but it's not abnormal from the perspective of the state machine.
But and why did it change? Because someone went there and wrote to the variable, or because there was a bit
Because,
in the
yeah,
memory?
imagine that there's been a bug in somewhere else which is written in the wrong place, for example.
Yes, but then we are not proposing a solution for all the problems, right? So if you
No,
have
okay, I'm not saying that you have to. I'm trying to understand what.
yeah, no, I don't have. No, go ahead. So if it's in the memory, if you can cause an event, for example, if you can protect a memory with a, let's say, a breakpoint of when someone writes on that memory, we can transform that breakpoint into instrumentation and say, okay, this range of memory, when it's written, it will cause me this breakpoint, and this breakpoint will create me one event. So I can say that only the task I know that should write can generate this kind of event, and then it could capture that.
Another possibility is that if, I mean, after you wrote that value, okay, if you have, a scenario where that value is only important when it is read back and used, okay, so when you, I mean, the code that is reading it back could be monitored, and therefore that value can also be checked in the monitor to be as expected, for example. It's not always the case, so it really depends on what you are monitoring, okay? So, like for example, in the Watchdog case, every time we pet, right, so the monitoring, the monitor can check the timeout retrieved from the hardware Watchdog to be less or equal to the FDTI, right? So why we did that with a specific failure mode in mind, right? So, but it depends on the beast that you are monitoring, right?
Yes, it's this kind of runtime verification is for event-driven system, right? If you have an event you can monitor, we can monitor. If you don't have an event we can monitor, we cannot monitor. It's not for RV. For example, RV is not for bit flip. Then you need to have other mechanism. It's only things that we can capture events.
Oh, okay, thanks for the explanation.
And okay, so next question is, with an external hardware watchdog, maybe even overwrite of the runtime verification monitor will lead to no hazard.
That's the thing that we capture from the safety application, right?
No, that is an hazard, because if you overwrite the runtime verification monitor states, then the monitor could be deactivated, right? So that is, and this is why we need to protect the states with end-to-end, for example. So that is yeah, that is not true, because we are losing the monitor safety mechanism. The other question is, it seems that the current RV monitor is monitoring some state-based behavior of piece of kernel algorithm in a particular context. Is the approach intended to be scalable and therefore accommodate the monitoring of other possible aspects of the kernel? For example, yeah, we can scale it to anything really. Like for example,
anything that generates events.
Yes. So for example, now I don't know, but for example, in the investigation that we are conducting in the OSCP working group and in the Linux feature for safety working group, you know, we could eventually, I don't know, but a possibility could be, you know, to have ad hoc monitors on the memory subsystem or on the around the mmstruct, you know, to monitor the events that are manipulating the process address space, for example. It's just an example, okay? So, but anything could be monitored, right?
Yeah, and anything you could trace can be monitored. That's it, the single phrase. Anything you can trace can be monitored.
And last question, we make it. We made it. So, how do you verify the correctness and integrity of the instrumentation implementation? Because because Daniel will implement everything up to ACLD standards, right?
Yeah.
No, well, seriously, no, jokes apart, if you notice, usually the code of the monitor itself is much more simple than the monitored subsystem usually. Okay, so, and this is the strength of this decomposition, right? But you know, usually when is it worth to apply this decomposition? When when the decomposed subsystem is simpler than the system before decomposition. Otherwise, it is not worth. And you know, this is I mean, we don't have the magic rod here, right? So it's still the same principle applies, right? So, and
yeah, I think I appreciate that, and I think it's I like the model, but in the end, you rely on the instrumentation in the kernel to drive your model. So how do you have confidence in that instrumentation?
No, that's not true, really. It's so no, that's not. So what you're saying is that the instrumentation is in the kernel is driving the design of the model itself.
No, it's driving the operation of the model. So you need to be certain that the events that are intended as inputs to the model are actually reflected, are actually kind of provided to you. So ultimately, you still need the events input from the instrumentation in order for your model to operate and do its job. So how do you kind of have confidence in that instrumentation?
You can either test the instrumentation or avoid instrumentation doing the calls for the monitoring directly from the subsystem. The only reason why we are not targeting that now is that we would have, it's easier to convince people to add instrumentation than to people to add the code straight to the code, to their subsystem. If people don't agree with instrumentation, I can just go there and do a direct call to the monitor and skip the instrumentation straight. You guys need to tell me what you guys want, and then I try to convince the maintainers, for example, of Watchdog subsystem. We can escape that part.
So you could have some kind of unit test within the unit test on the code to make sure that it actually works.
Yeah, yes. If unit test solves the problem of showing that instrumentation works, it's the
one way.
easiest
That's
part.
it. It's one way to do it. That's it. I don't have any good answers to this, but I'm just interested because that kind of seems to be the only gap.
If I agree, and my brute force answer would be, okay, let's skip the instrumentation, and I will add the calls to the monitor straight from C code from the monitored subsystem. But generally doing that is less generic. Maybe it's easier to convince the addition of instrumentation because it's useful for more purposes. But if the instrumentation will be a problem, for example, for the Watchdog subsystem, if it's a problem, then instead of adding a trace point to the Watchdog subsystem, I can go there, put an if-def RV enabled or that model enabled, call directly the model. And then I would skip instrumentation altogether. We can do that as well.
But it really depends on what is your solution space, because if you can define the hardware system, then you can also require that you will get a notification every now and then, even if it's a NOP. At that point, you can expect to have a maximum period for each event.
I didn't get that.
Let's say that if your notification is not fully asynchronous, meaning that if you can specify that you should get for each type of signal one event every maximum period, then you can rely on the fact that if you did not get any event for a specific signal, then there is a problem. Like,
Yes,
for example,
yes.
you will get a NOP event every 200 milliseconds.
Yeah, that's the thing that we have on the safety app. We can read the events back, and we use that as a feedback that the events are at least running before we go to the safe state. That's a way to. We are partially doing this already in the safety app. We are getting feedback and reading before say, okay, we are in the safe state, because we saw that the events that we expected executed. But instead of relying time, we are relying on the execution of the code as we expected.
So when it comes to missed events, we need to also figure out, like, system level mitigation, right?
And that's something I would like to get feedback. How hard it would be to show that the instrumentation is trustable or not. Because if it's not, I would change the RFC of the Watchdog subsystem to just go straight from the code and not add a trace point.
Okay, so I think we should leave some time to people to take a break before next session. Anyway, I enjoyed really much the discussion, and I really hope that we can continue this discussion about the runtime verification monitors also in the Paul working group and Elana's working groups, and because I think that we have some baseline to discuss further, and for some safety claims. Yeah.
Please try to get the information that unit test is enough for relying on instrumentation. That would be very good.
Excellent. Thank you very much. And very good presentation. And I'm just echoing some of the comments I'm seeing in the chat as well. So again, thank you very much, Daniel and Gabriele.
Thank you all.
And just to let people know, if they want to continue some discussion, the break room is open. And if people want to talk to others, they're welcome to join into the break room. And in the chat, Min has just posted a link. It's actually accessible from the schedule. Thanks, guys. Appreciate it. Bye-bye.